a device that is designed to bridge the gap between hardware and software connection to the cloud, enabling hobbyists, students, engineers, and even professionals to integrate an Internet of Things on any project much easier, therefore implementing it in a short period of time. Also, making data acquisition technology friendly to anyone without learning in-depth to the backbone and framework of the said systems. A system that would work on most demanding applications you need.
COVID-19 has been a difficult time for everyone, prohibiting us from seeing each other. Even in our dreams, we could not have imagined ourselves stuck in our homes with no outings and unable to meet our friends and relatives. But even though we can't see each other, we have found ways to continue with our daily lives far away from each other. In the current COVID-19 situation, when people are restrained physically, the internet has played a big role allowing people to work from home and keeping friendships intact by giving ways of communication. This is exactly what inspired us and the reason we came up with IoT DAQ. Just like how friendship remains intact through communication and how people can continue to work even from a distance, IoT DAQ aims to give you access to data, allowing you to communicate and control your device wherever you or your device may be. The team's goal is to design, develop, and implement an MCU-based Internet of Things data acquisition for monitoring and control system using cloud platform that bridges the gap between hardware and software. The objectives are to develop a device that is capable of extracting data, to use data acquisition technology in monitoring and controlling devices, to construct a device for online and offline controls, to implement a device that is equipped with a human-machine interface, to make use of API platforms to accelerate innovation, to integrate Internet of Things, and to make a device with analog and digital interface.
This device is a mirror device with the capability of communicating with each other, making it very useful in a wide variety of applications. Vital results of this device could be highly beneficial and significant, specifically to the following. One is agriculturists, logistics, security, electronic engineers, students, and lastly, future researchers.
This is the schematic diagram of IoT DAQ in multiple sheets.
So this is our chassis design. The size of 11.5 inches by 8 inches and the height of 4 inches.
Next is block diagram featuring integrated circuits. For our microcontroller, we use the APR ATmega2560, which is connected to our analog interface. Under DAC, or digital to analog converter, we have the AD5667 followed by the ADS1115, which is for our ADC. Next is digital interface. We have the GPIO, then the N-channel MOSFET, which is connected also to GPIO. The next is the internal access register. Here we have the MAX232 connected via UART. Then next is the online controls. We have the relay and also the N-channel MOSFET. Then next block is the Internet of Things, which we have the ESP32 connected via UART. Then the programming or debugging, which we use the Atmel ICE. Under this we have the human-machine interface, which is intended for offline controls. Here we use the Next-Gen Intelligence Series capacitive and assistive touch display, which has a 7 inches and connected to our relay, and channel MOSFET, and GPIO for monitor and GPIO for control. Then last is the external host MCU. We have the Arduino Nano connected via UART.
This is the bills of materials of IoT DAQ. IoT DAQ costs 26,305.957888 pesos for manufacturing a pair of IoT DAQ device. The specifications of IoT DAQ are as follows. 1. It has 4 maximum number of single-ended analog input channels, 6 maximum number of differential analog input channels, 860 maximum sample rate, 16 bits analog input resolution, 6 number of counters. In terms of software, any open source software, it uses C, C++, and Python. Connectivity, cloud, 5 volts absolute maximum voltage range, 2 amperes at 5 volts, maximum output current per line, RS-232 enabled, onboard display via 7 inches capacitive, AC driving and DC driving capability via relay and power MOSFET, and lastly, configurability via host MCU. The market price as of June 17, 2021 is 13,152.9789 pesos.
One of the amazing characteristics of our device is the easy-to-use and friendly user interface. The team used HMI, which also improved greatly so as to enhance easier interaction with the device. We are using the Next-Gen Intelligence Series HMI capacitive touch display with enclosure. We have here the barcode to our website, a short video, and the main menu. Basically, we have 7 menus or features. Under analog interface, we have the local device and the cloud device. We have here 4 channels on the local device and 4 channels also in our cloud device. Under digital interface, we also have here the local and the cloud device. There are 4 GPIOs for local device and 4 GPIOs also for our cloud device. Under online controls, we have here 2 relays and 2 MOSFETs. So you can control the relay 1 and relay 2 on and off by just clicking the button. And the MOSFET, you can control it by sliding the slider or clicking the add and subtract button. Under offline controls, menu 1, we have here digital inputs and digital outputs. So you can control the digital outputs by just clicking the on and off button. And for offline controls, menu 2, there are also 2 relays and 2 MOSFETs with a maximum value of 255 in MOSFET 1 and 2. For counters, values will appear here and you can clear the data by just hitting the button clear INT1 or clear INT2. The last feature is the internal access register, and this is used for the data that we cannot express in numerical values. We can also store data to cloud using the IAR. The number, the ID, and the subject are displayed.
This is the flowchart and functions of our device. The digital interface. This function uses 4-channel MOSFET for monitoring and control on and off devices. The analog interface gathers numerical data in the form of analog signals and makes use of those gathered data as it becomes a DAC output of the mirrored device. The online controls allows the user to control mirrored device with the help of internet. This function stores initial values, preventing loss of data. Offline controls menu 1. The first function in digital is that it monitors data of connected devices with the use of input values, provides output to control secondary device with the MOSFET or transistor circuits. Offline controls menu 2. allows the user to control the device itself with the use of relay and MOSFET circuits. Counters. This function allows the device to count signals, for example, in inventory. This function also has clear integer which allows you to start counting from 0. Internal access register. To read and store data that can't be expressed in numerical form, these data are also stored to the cloud.